In this video, we're going to be talking about resistors and resistance. And so when you're like building a circuit, most of the time you'll see resistors expressed as this kind of thing right here. But in reality, what they more look like is this thing right here, where the different colored bands represent different resistance values that you can have for a resistor. And the way it works is, so the current is like flowing through a wire, and then it goes up and it enters this sort of insulating material, something that the charges can't flow as freely through, and it causes them to kind of crash into each other and dissipate heat. But what it actually does is it lowers the current throughout the entire circuit. Through Ohm's law right here, we can see that the current and the resistance are actually inversely related. So by adding resistance, it decreases the current throughout the entire circuit.
So we're going to take a look at a circuit that has 3 different resistors. But we're going to keep in mind that all 3 of these resistors have the same resistance. So R1 equals R2 equals R3. These 2 resistors are in parallel. And if we combine these into an equivalent resistor, that one will be in series with R3. So to do this, we're going to look at this equation right here for R1 and R2 since they're in parallel. So if we do 1 over the equivalent resistance, that'll equal 1 over R1 plus 1 over R2. Since R1 equals R2, we'll get 2 over R, but we have to keep in mind that it's the reciprocal. So when we flip this, the equivalent resistance for R1 and R2 is R over 2. So once we have our R12 into one equivalent resistor, which is R over 2, and we have R3, we want to use this equation right here because they're in series. So the equivalent resistor is going to be R12 plus R3, which we just found that R12 is R over 2 and R3 is R. So we'll get 3R over 2 for the equivalent resistor for all 3 of the resistors. So once we get a circuit that's simplified to this, we're able to use Ohm's law to find current if we know the voltage of the battery. And keep in mind that the equivalent resistance is measured in ohms.
So far, we've only talked about circuits that have specific resistors in them, but something that's cool is that metals and almost all elements have inherent resistivity, which means that they have resistance just from the electrons within the material hitting against each other and creating heat and blocking the electrons from moving immediately. So the equation that describes this is R, which is resistance, equals resistivity, which is inherent to an element or a material, times the length of the material over the area of it. The resistance of metals and other conductors is going to be much lower due to its inherent resistivity. So, for example, copper, a really good conductor, really effective, is super low at 1.68 times 10 to the negative 8th ohm meters, while the resistivity of wood is very high at a magnitude of 1 times 10 to the 14th ohm meters. So clearly, copper will conduct electrons and flow a lot better than an insulator like wood will. So you can see here in this circuit, even though we don't have a resistor shown, in circuits like this, they will have an inherent resistance even if it's a conductor and it's very low.
Alright, so resistors have a lot of practical applications in the field of physics and engineering, and they're used in almost every kind of circuit to stop the flow of charges or to hold them temporarily. And so here you can see a normal circuit where V equals IR, and so with a real number for resistance and current, sorry, chopped the other part up. With a real number for resistance and current, V, I, and R are all normal numbers and in theory would be within a safe range, causing no explosion. But when V is I times approximately 0, if you just had a battery connected to a wire in your circuit, to try to move charges. Eventually the charges would just start circling around and around and around and around and around, and current would be roughly infinity if resistance is roughly 0 with any amount of voltage, which eventually would cause an explosion.
So now we will do a demonstration of a circuit with a battery and a resistor. The battery, Maggie, is very energized and shoots the charges with much enthusiasm, while Hannah, the resistor, slows down the current.
Whoa, man. We just gotta slow it down. We don't want to get out of hand here. I'm gonna throw them back to you real slow.
In order to keep
I don't want
a
it.
safe current level.